So what's the goal? Our goal for today? Well, we want to keep refining our understanding of motion. And motion is really important because it's our first hint of calculus in Calc 3. And so you probably should anticipate that you will see this sometime again in the near future. So we're going to start by introducing what's called the unit tangent vector. So I have a curve going through three-dimensional space. So we can even draw such a thing. So maybe I have my curve, here's my space, and I'm moving along here. So I could do something interesting as I move along, but I can ask what's happening at a particular point. So when I talk about a curve, we normally denote it as r of t. And of course, when I think about r of t, we should really think about it, it's saying a particle is moving along, it's a location, but of course we store things as vectors because then we can do calculus. And we like doing calculus. So we can ask about what's happening at a particular point. Say, maybe, let's go down here. Here's this point of a particular value, t naught. And I can ask, well, what's happening? What's the behavior? And one thing I can ask is, how is the particle moving? What's the motion? So motion, there's two aspects to it. There's the speed at which the particle is going, and we saw last time that we can use speed to find distance. But there's a second aspect, which is direction. So we can look at the tangent line, but in particular, if we look at r prime of t, that's the direction of the tangent line. That's pointing in the motion that the particle is currently going. Well, to make it really pure direction, we'll say let's make it into a unit vector. So r prime of t, that indicates where the particle is moving, but it stores two pieces of information, both the direction and the speed. And we're saying, look, I just want the direction. So divide out by the magnitude of r prime. That makes it into a unit vector. That's what we use to say what's the motion. Now, the philosophy of vectors is all vectors have two components to them. There's the magnitude, or the length, and the direction. And if you know both of those pieces, then you know the vector. So in particular, I can say that velocity is the magnitude of r prime, which is the length of the speed, and times this unit tangent vector. And it's very easy to convince yourself that this is true. Just come to this equation and move this magnitude of r prime across. All right. Well, let's do a problem. Find this unit tangent vector for a particular curve. So I have 1/2 t squared root 2t log t. All right. If I want to find the unit tangent vector, what should I do? Where do I start? Derivative? Start with the derivative, because you'll notice it's r prime. And so r prime, it's storing information about the tangent vector. All right. So r prime of t. Well, hopefully we're getting good at taking these derivatives. What do we get? T root 2, 1 over t. Okay. All right. Now, what's my next step?
Find its magnitude.
Find the magnitude, because I need to divide out by the magnitude. Okay, so magnitude, r prime of t. Well, so that's, magnitude is the square root, and then we square each entry. T squared plus root 2 squared, which becomes 2, plus 1 over t squared. Now, in some sense we could say we're done, but of course you should be suspicious, because I've left a very suspicious gap. Almost as if I anticipated something was about to happen. Well, this isn't just any example. This is a nice example. So t squared plus 2 plus 1 over t squared. What would we like to be true? We'd like to have a perfect square on the inside. Well, if you think about it, this looks like a square, because you can tell the square gives it away. This also looks like a square. So if you think of it, that's kind of like a squared, that's kind of like b squared. It'd be really cool if the middle were 2ab. Well, notice t and 1 over t actually are 1. So this is really the square root of t plus 1 over t squared. All right, so that becomes t plus 1 over t. Now, of course, after our last class, you're probably like, whoa, whoa, whoa. Now I'm going to throw absolute values everywhere. Okay, well, here we can assume that t is positive. They might say, why can we assume that? Notice the log of t function. There's no absolute value thrown into that. When can you take a log of a number? When it's positive. So there's sort of an implicit t is positive built into this function. And on a side note, this becomes t squared plus 1 over t. All right. Now that's the magnitude of r prime. We're going to be doing a lot of magnitude of r prime type things today. So we're going to get lots of practice. So how do you find, well, your new unit tangent vector? Well, you take r prime divided by the magnitude of r prime. Well, since the magnitude of r prime is a constant, dividing by the magnitude of r prime, I can flip it over. So 1 over the magnitude of r prime becomes t over t squared plus 1. And then I scale it by the original r prime. Oh, whoops. T root 2, 1 over t. I accidentally was copying r, no, r prime. And there you go. That's it. You can multiply it in, but you don't need to. There you go. Unit tangent vector. Now, what's our real goal? Okay, so we have a unit tangent vector, but where are we really going today? And the answer is, we're going to be focusing on acceleration. And in particular, our goal here is to look at taking acceleration and breaking it into 2 parts. And what are the parts? Well, we'll get to the picture in a moment. But let's start by looking at how do you find acceleration? Acceleration, it's the derivative of velocity. Yeah, we've known that for a long time. What's velocity? Well, very conveniently, we found a new way to write velocity as a magnitude times direction. So it's magnitude of r prime times this unit tangent vector. And they both depend on t. Well, now I have a derivative of a product. What rule do I use? Product rule. All right. So we use the product rule, which says take the derivative of the first times the second plus the first times the derivative of the second. Now comes the interesting part. I really have 2 vectors being added together because the product rule you end up with 2 parts. And in this case, each part is a vector. Let's think about where they point. Well, this first vector still has the same direction. It's the unit tangent vector. So where is it pointing? What? It's pointing on the tangent, yeah. And in particular, it's pointing where the particle is moving. So it's going with the motion. Okay, now, where does the derivative of the unit tangent vector point? Well, I'll tell you. It's a fun fact. It's perpendicular to motion. So the first part is parallel to motion. The second part is perpendicular to motion. Well, why is that? We'll get to that in just a moment. But what we're going to end up with is we're going to say, hey, we can always take acceleration and break it into 2 pieces. So every acceleration we're going to think of as saying there's one part of acceleration that's in the direction of our motion. Now when I say in the direction, it means parallel to some multiple of motion. So essentially when I'm parallel to motion, it's like pulling it forward and speeding it up, or maybe slowing it down depending upon the sign. Then there's a perpendicular aspect, and what the perpendicular aspect is it's trying to make it turn. It's trying to turn it to the side. So we can always take acceleration and break it into these two pieces. Our goal for today is how do we find how much of acceleration goes with motion, how much of acceleration goes perpendicular to motion. Okay, that's our goal. That's our goal. Now I have two notes here. Let's talk about the first one. And the first one is to justify this claim, perpendicular to motion. Now you might recall in a recent class, we said, hey, here's some interesting fact. If I have something which has constant magnitude, and I take the derivative, that's perpendicular to what I started with. So you might remember that we talked about it when we had like a ball. And we had this ball, and we said, hey, if I move on the surface of a ball, the motion of my motion is perpendicular to my location. Well, the fact that I'm always magnitude 1, I can think of as this is a vector that's on the surface of a ball. So that's why we know that the derivative is perpendicular to motion. So that's the justification for this claim. And since it's perpendicular to motion, there's some vector in that direction. We call it the normal vector. That seems a reasonable thing to call it. So that's where the n comes from. All right. Well, the second comment is what we've already said out loud, that these a sub t and a sub n, how much goes with the direction of motion, how much goes perpendicular to the motion. All right. Any questions about where we're going? Good. We are going to find a sub t and a sub n in two different ways, which is great. That's 200% more than what we need, but that's okay. It's good to know both. So let's talk about the geometry, and this is really going to help us get some intuition about what's going on with the picture. So let's draw the picture. Very conveniently ahead of time I drew the picture. So I have this curve, r of t, that's the green part. So I'm moving along this curve. And what I have is I've marked some vectors. So as I travel this curve, I pick a point. Here's my point. And then I say, well, there's this r prime of t. That's telling me my velocity. And r double prime of t, that's telling me my acceleration. Now you'll notice here that acceleration is pretty sort of almost, not exactly 90 degrees, but it's a pretty steep angle compared to velocity. The reasoning behind that is if you look, we're going around a turn. When you're moving along a straight line, velocity and acceleration more or less agree. But it's when you're turning, that tends to be the case when acceleration and velocity are starting to get a bigger angle between them. So what's going on? Well, I have in the picture here, this is my acceleration. So this r double prime of t is just another way to say my acceleration of time t. And what do I want to do? I want to break it into two parts. So the parts are what goes with motion. So it's this part here that's in the same direction as the motion. So this is the a sub t times capital T. I'm suppressing the of t's just for, well, to save myself some space. Then there's this second part that comes along here. And this part, this is your a sub n, capital N. And you'll notice that if I add these two together, it's the same as the original acceleration. So that's what we mean by decomposing. There's one part that's with motion, one part that's perpendicular to motion. Okay, that's not so bad. Now, I took this triangle here, and I've drawn it on the side. And I've marked the lengths. So I have the length with the motion. That's the a sub t. That's how much of motion goes, how much of acceleration goes in the direction of motion. There's this side, that's a sub n. How much is perpendicular to motion. This final side, that's your magnitude of your second derivative. Again, we could have put the magnitude of acceleration. So there's our picture. That's our understanding of what's going on. Well, let's think about what we have. We have this angle theta. It's been marked. It's the angle between my velocity and my acceleration. So let's start with finding the a sub t. So think of the triangle. What do we have? Well, we have the angle theta. We know the hypotenuse. We want the adjacent side. What connects those? What?
Cosine.
The cosine. Cosine connects adjacent and hypotenuse. Well, so we have the following. That the a sub t, it's the length of the hypotenuse times the cosine of the angle. So it's the magnitude of r double prime times cosine theta. Now, cosine theta, because it's the angle between r prime and r double prime, that shows up in a dot product, and we say, well, it's almost a dot product. It really is. The only thing that's missing is that magnitude of r prime. So we add in that magnitude of r prime. Like, oh, now it's not kind of like a dot product. It is a dot product. So it's r prime dot r double prime over the magnitude of r prime. So now we can find a sub t. If I know the velocity and I know acceleration, the answer is take the dot product of those two, divide by the magnitude of velocity. That is how much points in the direction of motion. This should hopefully not come as a surprise, because there's another way to think about what we just did. What we've done is we've done what's called projection. So it's projecting velocity, it's projecting acceleration onto velocity. And if you go back to the formula for projection, it involves a dot product. So we shouldn't be surprised to see a dot product when we have this situation here. All right. So that's a sub t. Well, let's think about a sub n. In this case, I have the angle, hypotenuse. I want the opposite side. What connects them? What? The sine connects them. I saw the sine, and it opened up my eyes. I saw the sine. Now, someone mentioned cross product. That's the right idea, because the sine of the angle between two vectors shows up in the cross product. And in particular, if I start with saying, look, I know my a sub n is the magnitude of r double prime times the sine of theta. Well, that's almost like the magnitude of the cross product if I add in this magnitude of r prime, so we do. And lo and behold, it's the magnitude of the cross product divided by the magnitude of velocity. And that's it. We've now found a sub t and a sub n geometrically. So we can do it in terms of dot product and cross product and put it all together, and life is good. Other than the fact that you have to do a dot product and a cross product and put it all together, that's a small detail. But other than that small detail, life is good. Okay, so that's method number one. Again, we'll pause to catch our breath and say, okay, any questions on this part?
Yeah,
Yes?
So are t and n, are those variables, or are they just like symbols like I, j, k were?
T and n represent tangent and normal. Now, what they are is they're the current tangent and normal directions. So we've been saving a little bit of ink. So when you see a t, you should really say in your mind, well, that's t, which depends on where I'm at. And when we write n, similarly, the direction depends on where I'm at. So acceleration varies as I move along the curve, which means that the t and n vary as I move along the curve. So they're functions of t. And they're vectors that depend on t.
Do you need to solve them occasionally?
I hope not. Oh, it's a dark day when you have to solve for them. No, they're not so bad. We solved for t before.
I thought that the tangent line and the acceleration were perpendicular to each other.
Not always. It just depends on the situation. So they can be perpendicular, and they are in some cases. So for instance, a case when you have that your acceleration is perpendicular to your tangent line, this is not too hard to check, is if you're on a circle. So if you're on a circle, and you're moving on a circle, let's say you're spinning around it, well, what turns out is that your direction of motion is going to be tangent to the circle, and your velocity is going to point straight to the center. So there are cases when that happens, but on the other hand, you could have a situation where you're doing something like this, where you're a car. Well, I'm not saying that you're actually a car, but imagine that you were a car, or you were in a car. Maybe that's a better thing to imagine. But imagine you're in a car and you're going down a track. Well, in that case, what happens is you start at 0, and then you start moving up. You speed up. Well, where's your velocity if you're going? The answer is your velocity is going forward with the car. Where's acceleration? Well, acceleration is also going forward with the car, because it's pulling you forward. It's making you speed up. So velocity and acceleration can be any angle between them. So it just depends on the situation, which is why we do the work. Isn't that fun? All these classes that don't make you work, what a terrible thing. All right, any other questions?
So if you wanted to know whether or not the acceleration was perpendicular to the velocity vector, would the dot product between r prime and r double prime be 0?
Absolutely. If you want to know if two things are perpendicular, you always just check the dot product. The dot product is 0, perpendicular. Not 0, not perpendicular. Of course, there's then a philosophical debate about, what about the 0 vector, but we won't get into that debate. Besides which, if we're going to get into a philosophical debate here at Iowa State, you have to have a lot of alcohol, apparently. Okay. Finding them algebraically. So we did geometric, dot products and cross products, and that's fantastic. Now, algebraically, and you might say, I love algebra. It's my favorite thing. That's why I took all these calculus classes, because I loved algebra so much. I just wanted another 3 semesters of it. Well, so there are some things to observe. So in fact, 2 observations. So let's talk about the first one. And we're going to have to go back a little bit here. Let's go back to when we talked about decomposing acceleration. If you look at it, you'll say this part, that's the perpendicular to motion part. Okay, so that's not going to be anything to do with my a sub t. And in particular say, hey, wait a second, I can match. I played the matching game before. These two things match. So that a sub t is the derivative of the magnitude of velocity. And at some point we have to find the magnitude of velocity anyways. So just do that. Find the magnitude of velocity, take the derivative, done. That's a sub t. How do you get a sub n? Well, now we come over here and say, wait a second, a sub t, we know that because we just found it. Magnitude of r double prime, we can find that. A sub n, well, that forms a triangle. So you have the magnitude of r double prime squared is a sub t squared plus a sub n squared. It's right triangle, Pythagorean theorem, useful theorem. We can find these two pieces, the magnitude of r double prime and a sub t, so that means we can find the third. Now you might say, well, hold on, do I know whether it's positive or negative? Because there's a square root. And the answer is it's always positive. Because if you look at where the a sub n came from, it's always a ratio of two magnitudes, which means it's a positive term. And that does the whole thing. So if you do that, you're done. And that's actually the whole thing. All right, so we will do both methods on at least one, possibly two problems, and compare. Now there's a few more notes, and let's just talk about these few notes. First off, the algebraically. There's this note that says this process works in all dimensions. Why do we make the comment? Well, if you come back over to the geometric side, you'll see we used a cross product. If I have a cross product, what dimension am I in? I have to be in dimension 3. This works in dimension 7, 9, whichever dimension you end up wanting to be in. So, you know, sometimes you have to feel a little sad for those 7-dimensional aliens who are like, oh, wouldn't it be great if we lived in dimension 3 and had that cool cross product, and the teacher's just shaking their head. No, no, no. Those poor dimensional 3 beings have no idea how awesome 7 dimensions are. So, but that's not for us to experience. We've talked about the unit tangent vector, the unit normal vector. Well, how did we find the normal direction? We took the derivative of tangent. Now, the derivative of the tangent vector is not a unit vector. It just has the right normal direction. It may not have the right length. So if I drop the word unit, t prime would be fine. If I want to make it a unit, I have to divide by the magnitude. So the normal direction is t prime over the magnitude of t prime. Almost never do we find the unit normal, but the book mentions these terms, so we'll throw them in just as a freebie. The binormal is found by saying, I want to be perpendicular to both. Well, if I want to be perpendicular to both, take the cross product of both. Now you might say, hold on, wait a second. You forgot to divide by the magnitude. Or did I? What's going to be the magnitude of the cross product?
1.
It's going to be 1. Why? They're both unit vectors. And if I want to take the magnitude of the cross product, in fact, we have an example on the other side. It's the magnitude of the two vectors times the angle between them. I started with two things which were perpendicular. Sine of the angle between them would be sine of a right angle, which is 1. This vector we have seen in some sense, it's the osculating plane. So if you look at the normal vector for the osculating plane, it's going to be in the binormal direction. This is an absolutely terrible way to find the normal vector for the osculating plane. You should never do it, but it can be done that way. Okay. Well, let's do some examples here.
So is a sub n the same thing as n function of t?
No.
No. Okay.
No. A sub n is a magnitude. Capital N is a direction.
All right.
So, here's an example. Find a sub t and a sub n for the following curve. Sine t minus t cosine t plus t, sine t, and t squared minus pi squared. So we have two approaches. There's the algebraic and there's the geometric. Which one should we do first?
Geometric.
Geometric. All right. Geometric. So for geometric, I'm going to need r. I'm going to need r prime. I'm going to need r double prime. So let's do r prime. All right, derivative of sine t. Cosine t, no big surprise. Product rule, okay. Derivative of t cosine t. Well, the derivative of the first would be 1. So minus the second, cosine t. And then I'll have t times the derivative of cosine t, which would be a minus sine t, but there's already a minus, so it becomes plus t sine t. Okay, so that's the first derivative. Oh my goodness. Okay, second derivative. Well, in the interest of time, I'll quickly fill it out. Minus sine t. Then derivative of t sine t, well, that's sine t plus t cosine t. And then you have derivative of t squared minus pi squared, which is 2t. What about the derivative of pi squared? How about that? 0. Okay, good. Just checking if you're awake. Now, maybe before I do the magnitude of r double prime, I should observe, hey, it's almost like this is set up to simplify, because it was set up to simplify. It's really t sine t, t cosine t, and twice t. Okay, now I can talk about r double prime. All right, back to you. Derivative of t sine t. What's the first entry? Sine t and t cosine t. Product rule. Derivative of t cosine t. Cosine t minus t sine t. Derivative of 2t. 2. All right, so I have my r prime and r double prime. So something else we should do, which is going to be required from both approaches, let's do the magnitude of r prime. Okay, so the magnitude of r prime will be the square root of t sine t squared plus t cosine t squared plus 2t squared, which is the square root of t squared sine squared plus t squared cosine squared plus 4t squared. And what does that become? It's 5t squared on the inside, because sine squared and cosine squared. So square root of 5t squared, which we'll write as square root of 5t. And just so no one heckles me, I'll assume t is greater than 0. So no one complains about absolute values. All right, so there's my magnitude. Good. Now, we said we were doing this geometrically first, so we'll get out our geometric color. No, there's no special geometric color, just switching colors. So if I want a sub t, I need to find the dot product. So r prime dot r double prime. So that's going to be t sine t, t cosine t, 2t dot sine t plus t cosine t minus t sine t, comma 2. So, taking the dot product, that would be t sine squared t plus t squared cosine t sine t. It's not a vector anymore. Sorry, that should just be parentheses. So that's the first term. Plus, second term, t cosine squared t minus t squared cosine t sine t. That's the next term. And then finally, 4t squared. Well, oh yeah, 4t. 4d. Yeah. Thank you. What happens? Some terms cancel out. T sine squared plus t cosine squared. It's t. And then there's another 4t, which makes 5t. Okay. Cool. Now, what do? Well, we need to find the cross product, r prime cross r double prime. So, we'll do that quickly. I, j, k, t sine t, t cosine t, 2t, sine t plus t cosine t minus t sine t, 2. So that will be I times t cosine t times 2. So that's 2t cosine t I. J times 2t times sine t plus t cosine t. So that's plus 2t sine t plus 2t squared cosine t j k t sine t times cosine t, so that's plus t sine t cosine t minus t squared sine squared t, and almost didn't make it, k. We're not done yet. We went down. Now to go up. Okay, so now it's sine t, t cosine t, and then t cosine t, but I'm subtracting. So minus. So that'll be t sine t cosine t, and then plus t squared cosine squared t. And that's, again, whoops, k. J, next term will be I. Then minus 2t cosine t minus 2t squared sine t I minus 2t sine t j. Well, if we're careful, which at this point I'm not sure if I have been, things should be nice. Those 2t cosine t's in the I direction cancel. 2t sine t's in the j direction cancel. T sine t cosine t in the k direction cancel. And what's left? Well, we have minus minus makes plus 2t squared sine t, comma. Then we have 2t squared cosine t, comma. And then I have a minus t squared sine squared and a minus t squared cosine squared, which makes this last entry minus t squared. All right, good. Now, if we were paranoid, what would we do? Nothing? No, because that means you're definitely not paranoid. That's the opposite of paranoid. But what would you do? Dot product. Even just one of them, right? Now you might say, wait a second, is it still true even when you have functions? And the answer is, yeah, it's still true. Let's cross our fingers. 2t cubed sine squared. 2t cubed cosine squared. So now what am I up to? Well, times 2t cubed, right? Minus 2t cubed is 0. Okay. Whew. Good enough. We'll assume the other one works too. Okay, cool. That's the cross product. Now, are we done? No, we're not done. What else do we need to do? We need to find the magnitude of the cross product. Okay, so the magnitude of r prime cross r double prime. So that's the magnitude of this vector, 2t squared sine t, comma 2t squared cosine t, comma negative t squared. So that is the square root of, square each entry, 4t to the fourth sine squared plus 4t to the fourth cosine squared plus t to the fourth. Well, what do the first two terms combine to? 4t to the fourth plus another t to the fourth makes 5t to the fourth, giving us square root of 5t squared. Okay. And we're still not quite done, but we're almost to the point where we can write down the answer. So here we go. A sub t is r prime dot r double prime over the magnitude of r prime. So we found the dot product was 5t. Is it still there? It is, right there. That's 5t came from the dot product. The magnitude of r prime is way back here. That's the square root of 5t. Okay, so that's, we'll move that up, square root of 5 times t. Put them together, what do you end up with? square root of 5. Okay, a sub n, that's the magnitude of r prime cross r double prime divided by the magnitude of r prime. So that's the square root of 5 t squared divided by the square root of 5 times t, which becomes t. Done. Look at that beautiful geometric solution. It just flows. You take all this stuff, you take the dot product, you take the cross product, and it works out nicely. Now we said we do it both ways. This was just one way. Ready for round 2? Round 2, here we go. We don't need that part anymore. We're doing algebraic. Now remember the algebraic, you still had to do all this stuff, but there was one other thing you needed for algebraic, but we'll get to that in a moment. All right. Now algebraic, a sub t, that's the derivative of the magnitude of r prime, which is the derivative of the square root of 5 times t, which is square root of 5. Done with that a sub t. Now you might say, that was faster. Well, that's just perception. We haven't done a sub n yet. Okay. Now a sub n, well, what do you have? Well, if you rearrange, you get a sub n squared. That's the magnitude of r double prime squared minus a sub t squared. Because a sub n squared plus a sub t squared, that's the magnitude of r double prime squared. So far, so good? Yeah, because it's true. Okay. Well, so that is equal to, I take the magnitude of r double prime, and I square it. So that's really just add up the individual terms squared. Sine t plus t cosine t squared plus cosine t minus t sine t squared plus 2 squared. So this part right here, that's the magnitude of r double prime squared. Okay? And it's not a fraction, by the way. This is a pointer. Okay? Yes? Just square up and add the entries. Doom, doom, doom. Minus, I have to square a sub t. Well, 5. That's a sub t squared. Okay. Well, here we go. So this becomes, got to square that, sine squared t plus 2t sine t cosine t plus cosine, t squared cosine squared t. Squared the first term. Plus cosine squared t minus 2t sine t cosine t plus t squared sine squared t plus 4 minus 5. Now, we hope a lot that things will simplify. Sine squared plus cosine squared, 1 plus 4, 5 minus 5, they all cancel out. 2t sine t cosine t minus 2t sine t cosine t, 0, cancel out. T squared cosine squared plus t squared sine squared, t squared. Okay, now that's not a sub n, that's a sub n squared. So how do I get a sub n at the end? Square root. So a sub n is t. Now, you're probably wondering, which way should I learn it? Should I learn it geometrically or should I learn it algebraically? And the answer is both. You should know both. In practice, I would say the algebraic tends to be faster. So if you're like, I don't know, in a time situation where you only have a small amount of time, you might say, let me just try to do the algebraic. But there are situations where the algebraic can be more painful. Now, I can't help but notice that our time is just about up, and we've only done 1 of 4 examples. So what I'll do is I'll actually record the other examples, and I'll explain what I mean by saying learn both. So if you want to know that, just watch the video. A few more examples, because these take some time, especially if you want to do it both geometrically and algebraically. So for the next one, let's do the following. We're going to decompose acceleration, which means we're looking for how much of acceleration is with motion, how much is perpendicular for the helix. This is something that we saw in our last lecture. So the helix given by cosine t, sine t, and t. So sort of this, almost like a spring. Well, so what do we do? Well, geometric. This will probably be a little bit more straightforward. So probably a little bit faster. So we need to have the following. Well, we need r prime. So take the derivative. Negative sine cosine 1. We'll need the magnitude of r prime. And what is that? Well, that's the square root of negative sine squared. So sine squared, cosine squared, and 1 squared, which combines to give square root of 2. We saw this before. The helix sort of goes at a constant speed. We'll need r double prime of t, and that will be derivative of negative sine is negative cosine, derivative of cosine is negative sine, and derivative of 1 is 0. And you'll notice that here the derivative is 0, and we can see that because if you think about the z component, the z part, it's t, which means that we're always moving up at a constant rate. So in the z direction, we're never slowing up, we're never, I guess you don't say slowing up, never speeding up, never slowing down. Okay, so now with these in place, what do we have? Well, we're going to need r prime dot r double prime. So negative sine cosine 1 dot negative cosine negative sine 0. So that's going to be minus sine t times minus cosine t. So that's sine t cosine t. Then cosine t negative sine t minus cosine t sine t. And 1 times 0 is 0. And aha! We get cancellation. 0. All right. That must mean something. We'll also need the cross product. R prime cross R double prime. Well, so we take the cross product. I, j, k, negative sine, cosine 1, negative cosine, negative sine 0. And we start working. I, cosine 0. Okay, 0i. j, 1, negative cosine, minus cosine j. K, negative sine, negative sine. So that's plus sine squared t k. Okay, we went down. Now we're going to go up. Here, negative cosine, cosine k. Well, we subtract. So it's minus cosine squared, so plus cosine squared k. Negative sine 1 and I. We went up, we subtract. So that becomes sine t I. 0, negative sine t j. That's 0 j. So we get sine negative cosine 1. Now, of course, you should probably check, is this in fact perpendicular? You can do the dot products. Minus sine squared, minus cosine squared, plus 1. Yeah, that's true, because sine squared plus cosine squared is 1. Here you'll get minus sine t cosine t, plus sine t cosine t, plus 0. Cancellation, perfect. Good, good. It all works out. Now, the other thing we need is the magnitude of r prime cross r double prime. Well, so that's the magnitude of this vector, sine t negative cosine t 1. And similar to what we did up there, that's going to become sine squared plus cosine squared plus 1, which is square root of 2. So, putting it together, we can now say that a sub t, which is r prime dot r double prime, over the magnitude of r prime, is 0 over root 2, which means that you get 0. And a sub n, well, that would be what? That's magnitude r prime cross r double prime over magnitude of r prime. So that's square root of 2, that magnitude of the cross product, over square root of 2, magnitude of r prime, which is 1. So that's the answer. A sub t is 0, a sub n is 1. And so in particular what this is saying is that the acceleration is always perpendicular to motion. Because that's what this 0 means. Look, none of acceleration happens with motion. All right, good, done. Now, you want to do it both ways to compare. Okay, so we can recycle. We can recycle because we still need these components here. All right, so we have that a sub t, if we do it algebraically, it's the derivative of root 2. Well, the derivative of root 2 is 0 because it doesn't change. It's a constant. All right, what about a sub n? Well, we know that a sub n squared is equal to the magnitude of acceleration, so that's the magnitude of the second derivative, minus a sub t squared. Well, we have the second derivative, so that would be the square root of cosine squared plus sine squared plus 0. And we just found acceleration, the a sub t, that's 0. All right, so we get square root of 1 minus 0, which is 1. And we're done. And lo and behold, they match. Now, all right, you're probably thinking, this was faster. You're right, it was faster. And it got the right answer. And again, you're right, it does get the right answer. So, okay, score 1 for both. They're both right. So, that's our first example we're going to talk about. Okay, next one. Find a sub t and a sub n for the curve r of t is t plus t squared, t minus t squared, 2t. Okay, so let's see what happens here. So again, we're going to do both geometric and algebraic. So we'll start, in fact, here we'll start with what we always need. You always need r prime. So that would be 1 plus 2t, 1 minus 2t, and 2. You need the magnitude of r prime, doesn't matter which method you're using. So that would be the square root of 1 plus 2t quantity squared plus 1 minus 2t quantity squared plus 2 squared. So this would be what? Well, I'm going to get ahead of myself. 1 plus 4t plus 4t squared plus 1 minus 4t plus 4t squared plus 4. And the 4t's cancel. And now you get some addition. 114 gives you 6. And 4t squared plus 4t squared gets you 8t squared. And there's not really much you can do with that. It is what it is. Square root of 6 plus 8t squared. Okay, that's fine. That's fine. R double prime. Well, second derivative. That'd be 2, negative 2, 0. Okay, so acceleration is actually, in some sense, always pointing in the same direction, as a constant direction. Okay, good. Now, what do we need? Well, we need to find a sub t and a sub n. And last time, we started doing geometric first, then did algebraic. We'll switch it this time. So we'll do algebraic first. So let's find magnitude of r double prime. So that would be the square root of 2 squared, 4, negative 2 squared, 4, 0. So that's square root of 8. Okay, so algebraic, say a sub t is the derivative of the magnitude of r prime, Well, that's the derivative of, and I'll write this as 6 plus 8t squared to the 1/2. So, chain rule, that's going to be 1/2, 6 plus 8t squared to the minus 1/2 times the root of the inside, 16t, which 1/2 times 16t makes 8t in the numerator, and then downstairs we're going to get square root of 6 plus 8t squared. Okay, so that's a sub t. Now, what about a sub n? Well, a sub n is going to be, well, let's do a sub n squared, magnitude of r double prime squared minus a sub t squared. Well, that would be 8. And then we're going to subtract the square of this. That's 64t squared over 6 plus 8t squared. Now, if we combine, we'll see that common denominator, this would be 48 plus 64t squared divided by 6 plus 8t squared. That would be the first term. Then we're going to subtract 64t squared, so minus 64t squared. Those cancel. And you get something relatively nice. Now that's a sub n squared. And therefore, we can conclude, so there's a sub t, that a sub n is equal to the square root of that. And what does that become? Square root of 48. Well, 48 is 16 times 3. So when I take the square root, I'll get 4 square root of 3 over the square root of 6 plus 8t squared. And there's a sub n. Good. Now, that was algebraic. Let's do it geometric. So for geometric again, we use a lot of the same materials. We'll need those parts there. And what do we do next? Well, we take our dot product and our cross product. So r prime dot r double prime, that's going to be 1 plus 2t, 1 minus 2t, 2 dot 2 negative 2, 0. So that would be 2 plus 4t, in those terms, then minus 2 plus 4t, so that's negative 2 and 1 minus 2t multiplied together, and 0. The 2's cancel. 4t plus 4t gets us 8t. The cross product, r prime cross r double prime, well, okay, so now we do a cross product. So that becomes I, j, k, put into the r prime, 1 plus 2t, 1 minus 2t, 2, r double prime, 2, negative 2, 0. So, here we go, I, 1 minus 2t, 0, that's 0i. J, 2, 2, 4j. K, 1 plus 2t, minus 2. So that's, well, I'll say plus, minus 2 minus 4t, k. Going the other direction. And then we're going to have 2, 1 minus 2t, k. So, but I went up, so that's like subtracting. So I'm going to write this as minus 2 minus 4t, k. Good. Minus 2, 2i. So that's minus 4i, but we went up, so we subtract, so it comes a plus 4i. And then 0, 1 plus 2t, j. That's 0j. We went up, so we subtracted. All right. So what do we end up with? We end up with 4 in the first entry, 4 in the second entry. In the last entry, the minus 4t's will cancel. And then we have minus 2, which is minus 4. So we get kind of a nice vector, 4, 4, negative 4. Now, what is the magnitude of this vector? Magnitude of 4, 4, negative 4. Well, we can actually simplify this to say, hey, this is really the magnitude of 4 times 1, 1, negative 1. Because I can pull out a common scaling factor, and then if I'm finding the magnitude, it says, well, look, take the size of this number, well, that's just 4. Now take the magnitude of this vector, which is the square root of 1 squared plus 1 squared plus negative 1 squared. So that's 4 square root of 3. We've seen these numbers before, 8t and 4 root 3. Of course we have, because we know that a sub t is equal to r prime dot r double prime over magnitude of r prime, which is 8t divided by magnitude of r prime, which we found over here, square root of 6 plus 8t squared. Good. And a sub n, that's the magnitude of r prime cross r double prime over magnitude of r prime. Well, we found the magnitude of the cross product, that's 4 root 3. And then magnitude of r prime, square root of 6 plus 8t squared. Again, done. All right. Well, okay. So we've done some examples and we're growing more and more convinced. Hey, they both work. We have these two ideas, these two approaches. Namely, we have the idea of the geometric and the algebraic approach. So here they are again, the geometric and the algebraic. Now, at this point, we might be tempted to say, hey, the algebraic approach is pretty quick because we don't have to do the cross products, and cross products can be very messy, especially when you start getting terms building up, more and more complicated expressions. And so you sometimes say, look, I don't even want to deal with the cross product. That's a very dangerous thing to do. But I want to give a word of warning. Which one of these should you know? And the answer is it's best to know both. In many cases, the algebraic approach can be pretty fast. But in some cases, it's better to use the geometric approach. Now let me sort of try to motivate why this is true. So why is it true that it's good to know both? And it comes down to sort of understanding one thing. Namely, this part. That's the one, and now of course I highlighted it so much you can't even see it, but what happens to the derivative of the magnitude of velocity? That determines everything. If the magnitude of velocity is really easy, in other words, it's a very simple expression, then it's really nice to just say, yeah, just take that magnitude of velocity, compute it, life is good, and keep going. However, what if the magnitude of velocity is messy? Then you run into trouble. And you say, okay, well, if the magnitude of velocity is messy, won't this other approach, this geometric approach, also be messy? And I'm going to try to give you an example. We'll see if it succeeds of how you can avoid messiness in some situations. And so in particular, we're going to construct an example now. And of course, this is dangerous to construct an example on the fly. If I were more confident, I would say, look, I'm a professional. Don't try this at home. I'm not quite that confident that the example I'm going to construct on the fly will be quite so nice, but that's okay. So here we go. Real life, real time example. So what we're going to do is we're going to find a sub t and a sub n, but in a very particular case. So we're going to say, let's find a sub t and a sub n for the following. Okay, so we just have to come up with a function, but we want to come up with a really unpleasant looking function, so we're going to sort of add lots of layers here. And as we do so, we should hopefully get people sort of like squirming. It's like, no, don't do it. It's not worth it. But we're going to persevere and keep going. So that's the first entry, 4t plus 2 minus sine 3t plus t e to the t. Then we'll have cosine of 2t. We'll put a 2 in front as well. And what else should we have? An arctangent of 3t. That's the last entry. Okay, the second entry. The third entry. All right, what do we need? Well, what haven't we done yet? Well, let's see. We can do a tangent of 2t again, and plus, so let's see, I have a little bit of space left. I'll say 2t squared. Good. There you go. So I want to find a sub t and a sub n for this. Now, right now, this is absolutely horrible. Would never want to do this problem, but I'm not quite done writing the problem. Second line says, at time t equals 0. Okay. Now we're going to come back to why this makes the problem not unreasonable. All right. So let's begin. Now, all problems begin the same way. We need r prime and we need r double prime. So I'm going to compute r prime and r double prime first. So let's see how we do. So this is r. So let's look at r prime. So that would be going through taking the derivatives. 4, here the derivative of sine is cosine, but the 3 comes out. So we're going to have minus 3 cosine of 3t. Then use product rule. So then we're going to have derivative of the first, so that would be e to the t plus t e to the t. Comma. Minus 4 sine 2t. Arctangent of 3t, well, that would be plus 3 over 1 plus 9t squared. All right, we're speeding up. Tangent of 2t, derivative of tangent of secant squared. So this will become 2 secant squared of 2t plus 4t. All right. Now, I think we'd all agree finding the magnitude of r prime is going to be messy, and finding the derivative of the magnitude of r prime is going to be worse. Well, it's not done yet. R double prime. What would that be? Well, taking the derivatives, 0 goes away. Derivative of cosine, negative sine. So this becomes plus 9 sine 3t. Then we have an e to the t. We're going to get another e to the t, so that's plus 2 e to the t plus t e to the t. Here we're going to get minus 8 cosine of 2t. And here, when we apply the chain rule, because really, how can you think of 3 over 1 plus 9t squared? It's 3 times 1 plus 9t squared to the negative 1 power. So if I think of it that way, then what this becomes is this becomes minus 54t over 1 plus 9t squared to the power 2. So that was the chain rule being applied. All right. Good. Next, with derivative of 2 secant squared of 2t, well, that becomes 4 times secant of 2t times the derivative of secant. Well, that's another secant tangent, and then plus 4. All right. Now again, if we were applying either approach, at this point it seems kind of hopeless, because there's r prime dot r double prime, there's r prime cross r double prime if we're doing geometric. Oh, that looks atrocious. On the other hand, if we're doing algebraic, we have to find the magnitude of r prime, take its derivative. We have to find the magnitude of r double prime squared. And this is just nuts. How can we do it? But then we remember, this is at time t equals 0. I don't have to find a sub t and a sub n for all values of t. That's what we've been doing so far. I have to find it for one specific value of t. Now, here's the beautiful thing. If we go back to the algebraic versus geometric. Now, if I was doing this in the algebraic approach, I have to take the derivative, which means I have to work with this as a function of t up through the point where I can take its derivative. So I can't evaluate until after I've done something very complicated. However, go back to the geometric. Notice that once we've actually found r prime and r double prime, if I want to know it at a specific point, I can evaluate before I do the dot product and the cross product. So now it comes down to the fact that, oh, wait a second, geometric evaluation can come before the operations that I have to carry out. Algebraic, no. You can't evaluate until after the derivative. So that's why here, geometric gives us hope. We have hope that we can finish this problem. So let's actually do the problem. All right, so let's separate. So we evaluate r prime at 0. So go through and plug in 0. What do you get? 4 minus 3 plus 1. Well, that's plus 0. So that's 2. Here you get 0 plus 3. 3. Here you get 2 plus 0. 2. So 2, 3, 2. What's our double prime evaluated at 0? Well, that is 0, cosine of 0, 0, 2, and 0. So it's 2 again. Then here you get minus 8 minus 0. So minus 8. Great. And then 4 times 1 times 0, so that's gone. So that's 4. And now, the rest of the problem, we never have to see a t again, because we evaluate before we take the cross products. You see, it doesn't matter whether you evaluate before the cross product or after the cross product, you're still going to get the same answer. So this comes to an idea of saying, when can I start evaluation? So if I'm looking at something at a specific time, evaluate when it's convenient. So we're almost done. We need a couple things. We need the magnitude of r prime. So that's the square root of 4 plus 9 plus 4, which is the square root of 17. We're going to need to know r prime dot r double prime. So that's 2 times 2, which is 4. 3 times negative 8 minus 24. 2 and 4 is 8. So that becomes 4 plus 8 is 12, minus 24, negative 12. And we'll need to know the cross product, r prime cross r double prime, I, j, k, 2, 3, 2, 2, negative 8, 4. Well, okay, so that's 12i, 4j, minus 16k. Then going the other direction, minus 6k, plus 16i, and plus 8j. Oh, excuse me, minus 8j, because I'm going the opposite way. We'll have to change the sign on that one. And yeah, I'm good. So it's minus 16i, so it becomes plus 16i. Yep. All right, so that would be 28, negative 4, negative 22. Now, I made a mistake, so I just want to double check to make sure I didn't miss another mistake. So 2 times 28 is 56. Then I'm going to subtract 12. That would be 44. Subtract 44 gives me 0. 56. Add 32. Give me 88. Subtract 88 gives me 0. Okay, good. So I fixed my mistakes. So now, what is the magnitude of r prime cross r double prime? Well, it's the square root of 28 squared plus negative 4 squared plus 22 squared. Whatever that turns out to be, it's a number. For our purposes, look, we just need a value. That's a value. So we can conclude the following. A sub t is the dot product over the magnitude. So that's negative 12 over square root of 17. And we just leave it like that. And a sub n, okay, that's square root of 28 squared plus 4 squared plus 22 squared, all divided by square root of 17. And we're done. Good. And that's it. So here is a case when it says, hey, if I'm evaluating on a specific time and I have something which is really messy, I can actually be better off using the geometric. In other words, using the dot product and the cross product. But on the other hand, there are times when it's like, hey, the magnitude of r prime is really clean. I get something nice and easy to work with. Use that method. So it's good to know both. We teach both methods because both methods can be useful in the right setting.